Hello from Slovenia. My name is Marjeta Čuk and I'm coming from University of Ljubljana, Faculty of Natural Sciences and Engineering, Department of Textiles, Graphic Arts and Design, Ljubljana. Today I would like to present you 3D printing and functionalization of textiles. By the end of this talk, you will be familiar with combining different technologies like weaving and 3D printing. First, I'll go through introduction and the aim of the study. Second, I'll talk about materials and methods. Then I'll show you the results and at the end the conclusions. This is our weaving lab, where the most of this project was done. On the left there is the mini-fiber laboratory loom with a teeth jacquard mechanism, where all the fabrics were woven, and on the right hand side there are computers with CAD programs. For this opportunity, this project, we also put there our 3D printer. 3D printing is used to produce individual objects or to print on different substrates to produce multi-component products. In the textile industry, we meet different uses of 3D printing. One is the printing of flexible structures based on rigid materials. Another is printing with flexible materials, and the third is the printing directly on textile substrate. All rigid, hard and soft or flexible materials can be integrated into the final design using 3D printing directly on the textile substrate. We speak of so-called multi-material objects and systems, which have many advantages, mainly in the increasing customization and functionalization of textiles or clothing. There are different 3D printing technologies, but fused deposition modeling technology is the most appropriate for printing on existing objects. Therefore, it is usually used for production of multi-material objects with textiles. FDM is the additive manufacturing technology based on material extrusion, in which a preheating station raises the temperature of the material, which is a polymer, to the melting point so that it can flow through a feed system. The polymer is fed into the system in the form of a thread. The most frequently used polymers for 3D printing with FDM technology are PLA, ABS, PETG, PT, and others. The aim of our research was to investigate the influence of the fabric structure, namely weave and thread density, which have the greatest influence on the fabric surface. In addition to the fabric surface, which is crucial for adhesion in 3D printing on textiles, the mechanical properties of woven fabric are also important for many applications, including a composite that can be used for protective clothing. Therefore, twill weave was investigated, whereas it has very good mechanical properties and highest tensile strength compared to the plain weave. 5 samples of polyester cotton twill fabric were designed in Arach Weave program and woven for the purpose of this research. 2 different weaves of 4-end twill are showed as technical diagrams with their labels on the right at the top. All samples were woven on mini-fiber laboratory loom with a teeth jacquard mechanism with the preset warp density 40 ends per centimeter and 3 different weft densities 15, 20 and 22 picks per centimeter. Black and white cotton yarns with a fineness of 8 by 2 tex were used for the warp and polyester blue yarn with a fineness of 33 tex for the weft. Physical properties such as yarn fineness, thickness, mass per square meter, reel warp and weft density were measured in accordance with the standards. The thickness of the fabric was measured with the fabric thickness tester in two ways. Thickness 1 was measured according to the standard, with the standard circular pressure foot. Thickness 2 was measured when the fabric was placed in the mounting frame prepared for 3D printing, because of a more accurate determination of the distance between the fabric and the nozzle. The 3D model was modeled according to the standard requirements in the open source 3D creation suite Blender and exported as STL file. The STL file was imported into the slicing software Voxelizer, where all parameters for 3D printing were set. The G-code was adjusted manually to avoid crashes of printing nozzle into the installation frame in which the fabric were inserted. All the samples were printed with the Z-Morph 3D printer with 1.75 mm PLA gray filament. Preliminary tests were done to define the nozzle temperature, the Z height of the nozzle, and the printing angle of the first layer. Z value was 0.35 millimeters, extruder temperature 210 degrees Celsius, bed temperature 60 degrees Celsius. Nozzle size 0.4 millimeters and layer height 0.2 millimeters. To define the exact positioning of the fabric on the printing bed, different methods of attaching the fabric to a printer bed were tested. On the left, there is attaching the fabric with a tape. In the middle, there is positioning of the mounting frame. And on the right, there is 3D printed object on a textile substrate still placed in the frame. T-peel adhesion tests were performed according to standard. Using an Instrom dynamometer, the separation rate was 100 mm per minute. In all cases, the measured warp density increased compared to the preset on-loom value, most pronounced for the fabric K13Z22 by 3.75%. The measured weft densities for the fabrics with the preset on loom weft density 15 px per centimeters stayed the same or decreased slightly, while the measured weft densities increased for the fabrics with 20 or 22 px per centimeter preset weft density. The increase was the highest for the sample K13Z22 with 14.55%. With increasing weft density, the aerial weight increased, while the thickness 1 and the thickness 2 decreased. Here represented maximum adhesion forces and standard deviation on 3D printed textile substrates with the same width and different weft densities. Stripped bars in the figure indicate that the fabric ruptured during adhesion test before 3D printed object was detached from fabric. The highest adhesion force was achieved at the lowest weft density at both widths, and the lowest adhesion force was achieved at preset weft density 20 px per centimeter and the broken twill 1.3. The highest standard deviation was calculated at broken twill and preset weft density 15 px per centimeter. and the lowest a twill 1,3 at preset wave density 22 pixels per centimeter. Dependence of the adhesion force on the mass for different samples shows that for the same width, the adhesion force decreases with increasing mass. Comparing all the samples, a change in the mass of the samples has no direct influence on the change in the adhesive force. But there is a general tendency that the adhesion force decreases with increasing mass. Here, the dependence of the adhesion force on the thickness of the fabric, measured according to the textile standard on the samples, is shown that the adhesion force increases with increasing thickness. The adhesion force decreases with increasing wave density for the same width. Comparing all samples, the tendency is that the adhesion force decreases when the measured wave density increases, but the correlation is not direct. An increase in the measured warp density also shows a general but not direct tendency for the adhesion force to decrease. The adhesion of the 3D printed objects to textiles is influenced by many factors. Preparing of a 3D model for printing, setting up the printer, placing the fabric on the printing table, and of course the construction parameters of the fabric. The results obtained show that any change affects the adhesion. In general, we have found that the density of the fabric has the greatest influence on the adhesion force. If you observe the differences between the widths, we find that the highest adhesion was achieved with a broken twill 1,3 at the preset wave density of 15 threads per centimeter. Results show that the adhesion force increases with increasing thickness. The fabric thickness, measured according to the textile standard, generally increases with decreasing wave density, which leads to longer floats on the warp threads and to larger available yarn surface for polymer adhesion. In further research, it is therefore important to determine the maximum adhesion force of 3D printed objects on textiles suitable for protective clothing. Thank you for your attention.